Baik, selamat malam semuanya. Sebentar saya coba untuk share screen. Oke, baik. Selamat malam semuanya, karena kemarin materi PCA yang pertama itu masih belum selesai, jadi kita masih belum bahas part yang kedua. Maka kita hari ini akan melanjutkan terlebih dahulu materi yang pertama kemarin untuk yang part 2 yaitu inner product. Apakah layar saya sudah terlihat? Oke, baik, sudah ya. Oke, kita lanjut materi yang kemarin untuk inner product. Nah, jadi objektif pembelajaran untuk inner product itu adalah memahami apa itu inner product. Yang kedua, mengetahui sudut dan jarak dengan menggunakan inner product. Yang ketiga, menulis kode untuk menghitung jarak dan sudut antar data. Yang keempat, memahami properti inner product. Yang kelima, mengetahui bahwa orthogonality tergantung pada inner product. Oke, kita next. Nah, kalau untuk dot product ini kayaknya di pertemuan awal-awal itu kita udah bahas ya untuk dot product. Coding langsung untuk dot product yang menggunakan fungsi bawaan untuk langsung kita panggil dot product-nya gitu hasilnya. Oke, jadi di sini inner product, dot product generalisasi itu dijumlah semua, jadi ada panjang, instant, sama si ini angle. Panjang, distance, sama angle. Panjang, distance, sama angle itu dijumlah semua. Kita coba lihat ya. Ini oke, di sini ada contohnya kan untuk cos alpha sama dengan dari atas x pangkat t per pangkat y sama dengan yang ini sigma n i sama dengan 1 xi yi, x, y, eirn. Oke, jadi kalau di inner product itu nanti hanya kalau udah kita dapat perhitungannya itu nanti kita akan tahu generalisasi dari jumlah semua panjang, distance, sama angle. Terus baru kita cari gimana cara kita dapetin si panjang, distance, dan angle itu gitu dari dimensinya. Nah, itu pakai yang tadi cos alpha tadi. Yang ini ya, ini untuk kita tahu gimana kita dapetin panjang dan yang lainnya itu ya. Jadi ini dapat 0,64 radian gitu. Ini untuk rumusnya kita tahu dapat kita cari tiga yang tadi panjang, distance, dan angle-nya itu. Terus dot product ini rumusnya vektor dot product AB sama dengan AB cos theta. Cos theta A kali B AB. Jadi sama ya sama yang ini. Itu untuk kita cari gimana kita dapat si dimensi yang tadi itu ya, yang panjang, distance, angle. Oke, itu. Jadi kita tinggal masukin rumus yang ini. Jadi tadi kalau dari gambar yang ini kan kelihatan A-nya, B-nya, terus dapat juga θ-nya. Terus hasil akhirnya ini ya 4,5. Atau setara dengan 0,64 radian. Oke. Bentar, saya coba buat share sound dulu.
This is Mr. Martin. These are video notes for Pre-Calculus Advanced. We're in Unit 9. I know this says 5, but we're in Unit 9. And we're continuing talking about vectors. We're going to be talking about dot product, angle between two vectors, and we're going to look at an example of work. Starting with dot product, in the video we're going to learn actually how to calculate this, and then we'll continue our discussion in class about what the dot product actually means. It's a strange concept, but you'll use it in physics. Again, we'll just learn how to calculate the dot product in the video. So if we have two vectors, vector v, which is ai plus bj, and w, which is a2i plus b2j, then the dot product v dot w, notice we say this v dot w, that's how we say that. It's not really multiplication. It's kind of a new operation that combines addition and multiplication. It's defined as a1 times a2 plus b1 times b2. So we're multiplying the two x components, and we're multiplying the two y components, and then we're just adding those up together. So if you'll notice, what we end up with here is a scalar quantity. It has no associated direction. We take two vectors, we calculate the dot product, and we end up with a scalar quantity. So if you want to take a look at this first example and give these a try, based on the formula up above, feel free to pause the video and try those. Otherwise, I'm going to work through these. And if you do try them, you can follow along and check your answers afterwards. Okay, so the first thing that I'm going to do, because I personally prefer to work in component form, so I'm going to just change this to 2, -3, and I'm going to change this to 5, 3. All right, now since we're doing v dot w, so again, the formula is to multiply the x components, so I have 2 times 5, and I'm going to multiply the y components, so that's -3 times 3, and then we just simply add those up. So we get 10 minus 9, which is equal to 1. So the dot product of these two vectors is the scalar quantity 1. All right, again, anytime you feel like you got the hang of this and you want to pause the video, and then you can restart it to check your answers, feel free to do that. So now we're going to do v dot v. We're going to do the vector dot product with itself. So now we're going to have 2 times 2, because that's the x component of v times the x component of v, and -3 times -3, that's the y component of v multiplied by itself, and then we'll just simply add those up. So we get 4 plus 9, or 13. All right, now let's try w dot w. So that's going to be 5 times 5 plus 3 times 3, or 25 plus 9, which is 34. All right, now these last two examples are kind of special cases here. So let's go ahead and let's find the magnitude of v. So we know the magnitude of v is going to be the square root of the sum of the square of the two components. So that's going to be 2 squared plus -3 squared. So that's going to be the square root of 4 plus 9, which is the square root of 13. Okay, so we can see that when we do v dot v, we got 13. When we find the magnitude of v, we get the square root of 13. So really, I could find the magnitude of a vector by doing its dot product with itself and then taking the square root. So something to keep in mind. As always, if you have questions about these, make sure that you ask. All right, moving on to angle between two vectors. So if u and v are two non-zero vectors, then the angle theta, we're going to measure this angle between 0 and pi between u and v is determined by the following formula. So we've got that the cosine of theta is u dot v, so here's an application of dot product, over the product of the magnitude of u times the magnitude of v. All right, so when we're finding angle between vector, we've got three things that we need to find. We need to find the dot product, and we need to find the magnitude of one of the vectors, and we need to find the magnitude of the other vector. Okay, and then at the end, don't forget, in order to solve for theta, we're going to have to take the cosine inverse of both sides. So there are other ways you could find the angle between two vectors. You could find the angle that each of them forms with the positive x-axis and then subtract it. This is going to be a much easier way. If you feel like you want to try these examples again, please go ahead and pause the video. Otherwise, I'm going to go through these with you. So I'm just going to draw a little sketch because this helps me visualize what's going on. So I have 4, -3. So here's the first vector. And then I have 2, 5. So here's 2, 5. And when I talk about the angle between the two vectors, what I'm talking about is finding this angle here. Okay, so we always want to find the angle that's going to be less than 180, or between 0 and 180. Again, if we go back to our definition here, between 0 and pi, between 0 and 180. All right, so our formula says that the cosine of theta, we're going to call this theta here, is going to be u dot v divided by the product of the magnitude of u times the magnitude of v. All right, so I've got u dot v. I'm going to do some calculations on the side. Again, I'm going to multiply the x components, so that's 4 times 2. I'm going to multiply the y components, -3 times 5, and then I'm going to add those. So I get 8 minus 15, so the dot product of these is -7, and then I need the magnitude of u, so that's going to be the square root of 4 squared plus -3 squared, which is the square root of 16 plus 9, that's 25, and the square root of 25 is 5. And I also need the magnitude of v, so that's going to be the square root of 2 squared plus 5 squared, so that's the square root of 4 plus 25, which is the square root of 29. All right, so now that I have all of this, I can substitute it into my formula, and I'm going to take the cosine inverse of both sides as well. So I know that theta is going to be the cosine inverse of u dot v was -7, and the magnitude of u was 5, and the magnitude of v was square root of 29. And if I substitute all this into our calculator, we're going to find the answer in degrees. So we'll find that, make sure your calculator's in degree mode, then we will end up with 105.1 degrees. All right, so why don't you go ahead and pause the video and see what you can do on the next example here, and then when you restart the video, I'll have the solution there for you, and you can double check and see what you did if you didn't get it right. actually go ahead and you can go ahead and do the next two examples. So pause the video now and try these examples, and then you can check them when you're done. Alright, so if you pause the video and work this out, you should have gotten 150.7 degrees. So here's a little sketch. You can see this angle looks like it could be about 150 degrees. So the dot product of u and v would be negative 41, and then the magnitude of u is square root of 34, and the square root of v is square root of 65. If these did simplify, really there's no reason to simplify them because we're going to be plugging it into this calculation here. So it's easier just to leave them as unsimplified radicals. And then when you calculate this all out, you should get 150.7. Again, make sure you ask questions if you have them. Now, for this one, this is an interesting case because when we did u dot v, we get 0. So I've calculated the magnitude of u and v, but we really don't have to because we're going to end up with u dot v, which is 0 over some number. So 0 over some number is just 0. And we know that the cosine inverse of 0, meaning what angle between 0 and pi has a cosine of 0, well, that's up at the top at pi over 2 or 90. So what this means is these two vectors, are perpendicular. All right, and this is an important concept that we have, and we're going to have a word for this perpendicular. When two vectors are perpendicular, we say the vectors are orthogonal. Okay, so here's another vocabulary word. So if I give you a problem and it says determine if the vectors are orthogonal, you want to see if they are perpendicular. If they're perpendicular, their dot product is going to be 0. Okay, so keep that in mind. New concept here in this example, another vocabulary word. Again, if you have questions, make sure you ask. And let's move on to this last example here. It says a Boeing 737 aircraft maintains a constant airspeed of 500 miles per hour in the direction due south, which means directly south. So for this direction here, if we're thinking about this on a coordinate grid, this would be negative 90 degrees. Okay, the velocity of the jet stream is 80 miles per hour in a northeasterly direction. Okay, so for this one, we could think of this, it's north and east, so this would be 45 degrees. Find the actual speed and direction of the aircraft relative to the ground. So I'm going to draw a little picture here. And I've got the airplane is going directly south at 500. And the wind is blowing at 80 miles per hour at 45 degrees. And we want to find the actual speed and direction. So why don't you go ahead and give this a try. This is kind of a review from the last section. So you should be able to do this. Basically, we're finding the resultant velocity and direction, which you should be able to do. So pause the video, and I will have a solution for you at the beginning of the next video so you can check. So we'll see you there.
Oke, ini untuk tadi penjelasan dot product angle di dalam vektor ya. Oke, sebentar, kayaknya dulu tuh pernah ya bahas tentang dot product untuk langsung coding. Di Python. Sebentar, kita coba lihat dulu demonya. Karena di hari yang kedua ini kita cuma full video karena materinya cukup berat, dan kalau yang jelasin trainer kayaknya ini lumayan panjang, jadi kemarin kita nemu beberapa video yang bisa jelasin langsung detail. Terus untuk yang PCA pertama yang ini, yang tentang dot product ini nggak ada codingnya gitu tadi aku lihat, tapi setahu aku kita pernah bahas tentang dot product di materi awal. Oke, iya benar ya. Ini udah ada dot product di waktu materi awal nih. Dot product sama scalar multiplication. Kita coba dari sini aja. Kayaknya kalau ini terlalu susah juga ya dipahamin buat ini ya. Multiplication, division 2 vektor. Nah, yang ini. Vector dot product. The vector dot product performed between the two same length sequential vector and return the single dot product. We will use the titik dot. Jadi kita pakai metode yang ini untuk perform dot produknya gitu. Jadi kalau buat yang ini, kayaknya kita juga harusnya pakai dot product langsung bisa sih. Oke, itu nanti bisa dibuka-buka lagi ya untuk codingannya yang udah pernah dot product. Oke, terus inner product definition and properties. Simetri. Ini ada simetri. Itu order doesn't matter. X, Y. Di simetri yang ini ya, X, Y sama dengan Y, X. Terus positif definite itu positif gitu ya, pakainya positif, definite positif. Terus bilinear. Di bilinear ini ya X, Y, Z, V, lambda, X, IR. Inner product length of vector. Jadi lambda X sama dengan lambda X. Lambda X sama dengan lambda X kali X. Oke, lambda X kali X. Untuk yang X plus Y, itu yang X plus Y. X plus Y itu triangle inequality. Kalau yang X, Y kurang dari sama dengan X kali Y, itu ada di yang Cauchy-Schwarz inequality. Ya. triangle inequality sama Cauchy-Schwarz inequality. Nih, lambda X sama dengan lambda kali X. Terus di distance between vector itu yang D X, Y ini X kurang Y. Ini untuk distance between vector. Terus untuk angle integral angle pakai yang ini ya. Kemarin yang ini angle itu juga udah pernah dibahas orthogonality ya dulu di materi matematika sebelumnya juga. Jadi yang ini ada X, ada Y, terus kita hitung pakai cos. W sama dengan X pangkat T Y per XY. Kita tahu X sama Y-nya. Terus kita cari cos W-nya. Orthogonality. Angle dan orthogonality. Unconventional inner product for function will be advanced. Oke. Integral to null orthogonal. Oke, ini yang unconventional lanjutan yang tadi. Ini full playlist buat yang kita pembahasan tentang PCA bisa ditonton nanti. Oke, di sini nggak ada sama sekali nggak ada codingannya tentang dot product ya. Ini yang dulu sempat kita pelajarin dot product yang ini itu mungkin bisa dibaca-baca lagi sama dilihat untuk penerapannya yang lain tuh dot product gimana gitu ya untuk di Python-nya. Terus nanti kalau udah di bagian PCA yang hari ketiga itu nanti juga ada mulai vektor scalar dan yang lainnya. Oke. Ini di linear algebra 1, nanti bisa dilihat lagi. Terus untuk materi hari kedua ini itu full video ternyata, tadi udah dicek. Karena memang materinya cukup berat di PCA itu harusnya materi untuk S3 sebenarnya. Tapi kita disuruh jelasin untuk yang PCA ini lumayan berat gitu. Jadi kita lumayan takut kalau bingung nanti jelasinnya dan nggak nyampe. Jadi di sini dikasih video yang emang udah jelas banget, udah detail banget dan lebih mudah dipahami. Jadi agenda hari ini kita tentang ortogonal. Oke. Iya, betul. Materi S3 kayak nanti singular value decomposition itu juga sebenarnya materi S3. Dari yang sebelum ini ikut dari yang kayak organisasi-organisasi beberapa kampus, saya ikuti organisasi beberapa kampus, itu juga nggak berani membahas PCA karena itu materi S3 gitu. PCA, singular value decomposition itu juga dibahas kupas tuntas semua di S3. Seperti itu.
Let's say I have a line that goes through the origin. I'll draw it in R2, but this can be extended to an arbitrary Rn. Let me draw my axes. Those are my axes right there. Not perfectly drawn, but I think you get the idea. Let me draw a line that goes through the origin here. So that is my line there. And we know that a line in any Rn, we're doing it in R2, can be defined as just all of the possible scalar multiples of some vector. So let's say that this is some vector right here that's on the line. We can define our line. We could say L is equal to the set of all the scalar multiples. Let me say that this is vector Let's say that that is v right there. So it's all the possible scalar multiples of our vector v, where the scalar multiples, by definition, they're just any real number. So obviously, if you take all of the possible multiples of v, both positive multiples and negative multiples and less than 1 multiples, fraction multiples, you'll have a set of vectors that will essentially define or I guess specify every point on that line that goes through the origin. And we know, of course, if this wasn't a line that went through the origin, you would have to shift it by some vector. It would have to be some other vector plus CV. But anyway, we're starting off with this line definition that goes to the origin. What I want to do in this video is to define the idea of a projection onto L of some other vector x, So let me draw my some other vector x. Let's say that this right here is my other vector x. Now, a projection, I'm going to give you just a sense of it, and then we'll define it a little bit more precisely. A projection, I always imagine, if you had some light source that were perpendicular somehow or orthogonal to our line. So let's say our light source, the light was shining down like this, and I'm doing that direction because that is perpendicular to my line. I imagine the projection of x onto this line is kind of the shadow of x. So if this light was coming down, I would just draw a perpendicular like that, and the shadow of x onto L would be that vector right there. So we can kind of view it as the shadow of x on our line L. That's one way to think of it. Another way to think of it, and you can think of it however you like, is how much of x goes in the L direction. But the technique would be the same. You draw a perpendicular from x to L, and you say, okay, then how much of L do I have to go in that direction to get to my perpendicular? Either of those are how I think of the idea of a projection. I think the shadow is part of the motivation for why it's even called a projection, right? When you project something, you're kind of beaming light and seeing where the light hits on a wall, and you're kind of doing that here. You're beaming light and you're seeing where that light hits on a line in this case. But this isn't you can't do anything with this definition. This is just kind of an intuitive sense of what a projection is. So we need to figure out some way to calculate this, or a more mathematically precise definition. And one thing we can do is, when I created this projection, let me actually draw another projection of another line, or another vector, just so you get the idea. If I had some other vector over here that looked like that, the projection of this onto the line would look something like this. You just draw a perpendicular, and its projection would be like that. So I don't want to draw, for just this case, I want to give you the sense that it's the shadow of any vector onto this line. So how can we think about it with our original example? Well, in every case, no matter how I perceive it, I dropped a perpendicular down here. And so if we can construct a vector right here, we could say, hey, that vector is always going to be perpendicular to the line. And we can do that. I wouldn't have been talking about it if we couldn't. So let me define this vector. Actually, I'm not even going to define it. What is this vector going to be? If this vector, let me not use all these thises. Let me say that this vector, we know we want to somehow get to this blue vector. Let me keep it in blue. That blue vector is the projection of x onto L. That's what we want to get to. Now, one thing we can look at is this pink vector right there. What is that pink vector? That pink vector that I just drew, this is x. That's the vector x minus the projection, minus this blue vector over here, minus the projection of x onto L. Right? If you add the projection to the pink vector, you get x. So if you add this blue projection of x to x minus the projection of x, you're of course going to get x. And we also know that this pink vector is orthogonal to the line itself, which means it's orthogonal to every vector on the line, which also means that its dot product is going to be 0. So let me define the projection this way. The projection, this is going to be my slightly more mathematical definition. The projection of onto L of some vector x is going to be some vector that's in L, right? I drew it right here, this blue vector. I'll trace it with white right here. Some vector in L where, and this might be a little bit unintuitive, where x minus the projection vector, x minus the projection onto L of x, is orthogonal is orthogonal to my line. So I'm saying the projection, this is my definition. I'm defining the projection of x onto L to some vector in L where x minus that projection is orthogonal to L. This is my definition. And that is a little bit more precise, and I think it makes a bit of sense why it connects to the idea of kind of the shadow or a projection. But how can we deal with this? I mean, this is still just in words. How can I actually calculate the projection of x onto L? Well, the key clue here is this notion that x minus the projection of x is orthogonal to L. So let's see if we can use that somehow. So the first thing we need to realize is, by definition, because the projection of x onto L is some vector in L, that means it's some scalar multiple of v, some scalar multiple of our defining vector, of our v right there. So we could also say, hey, look, we could rewrite our projection of x onto L. We could write it as some scalar multiple times our vector v. Right? We can say that. This is equivalent to our projection. Now we also know that x minus our projection is orthogonal to L. So we also know that x minus our projection, and I just said that I could rewrite my projection as some multiple of this vector right there. I mean, you could see it the way I drew it here. It almost looks like it's 2 times this vector. So we know that x minus our projection, this is our projection right here, is orthogonal to L. Orthogonality, by definition, means its dot product with any vector in L is 0. So let's dot it with some vector in L. Well, we can dot it with this vector v. That's what we use to define L. So let's dot it with v. And we know that that must be equal to 0. We're taking this vector right here, dotting it with v, and we know that this has to be equal to 0. That has to be equal to 0. So let's use our properties of dot products to see if we can calculate a particular value of c. Because once we know a particular value of c, then we can just always multiply that times the vector v, which we are given, and we will have our projection. And then I'll show it to you with some actual numbers. So let's see if we can calculate a c. So if we distribute the c, if we distribute the v, we know the dot product exhibits the distributive property. This expression can be rewritten as x dot v, right? X dot v minus c times v dot v, c times v dot v. I rearrange things. We know that c minus cv dot v is the same thing. We could write it as minus c times v dot v, and all of this, of course, is equal to 0. And then if we want to solve for c, let's add c v dot v to both sides of the equation, and you get x dot v is equal to c times v dot v. Solving for c, let's divide both sides of this equation by v dot v. You get, do it in a different color, c is equal to this x dot v divided by v dot v. Now what was c? C was, we're saying the projection of x, let me write it here, the projection of x onto L is equal to some scalar multiple, right? We know it's in the line. We know it's in the line, so it's some scalar multiple of this defining vector, some scalar multiple of the vector v, and we just figured out what that scalar multiple is going to be. It is going to be x dot v over v dot v. And this, of course, is just going to be a number, right? This is a scalar still. Even though we have all these vectors here, when you take their dot products, you just end up with a number. And you multiply that number times v. You just kind of scale v, and you get your projection. So in this case, the way I drew it up here, my dot product should end up with some scaling factor that's, maybe close to 2. So that if I start with a v and I scale it up by 2, this value would be 2, and I'd get a projection that looks something like that. Now this looks a little abstract to you, so let's do it with some real vectors, and I think it'll make a little bit more sense. And nothing I did here only applies to R2. Everything I did here can be extended to an arbitrarily high dimension. So even though we're doing it in R2, and R2 and R3 is where we tend to deal with projections the most, this could apply to Rn. So let me do it as a particular case. Let me define L. Let me define my line L to be the set of all scalar multiples of the vector, I don't know, let's say the vector 2, 1, such that all of them are, the c is any real number. So let me draw my axes here. That's my vertical axis. This is my horizontal axis right there. And so my line is all the scalar multiples of the vector 2 dot 1. And actually, let me just call my vector 2 dot 1. Let me call that right there the vector v. So let me draw that. So I go 1, 2, go up 1. That right there is my vector v. Vector v right there. And the line is all of the possible scalar multiples of that. So let me draw that. So all of the possible scalar multiples of that, you just keep going in that direction, or you keep going backwards in that direction, or anything in between. That's what my line is. If we just, all of the scalar multiples of my vector v. My vector of my vector v. Now let's say I have another vector x. Let's say I have a vector x. And let's say that x is equal to 2, 3. So let me draw x. X is 2, and then you go 1, 2, 3. So x will look like this. Vector x will look like that. Well, let me draw a little bit better than that. Vector x will look like that. That is vector x. And what we want to do is figure out the projection of x onto L. And we can use this definition right here. So let me write it down. The projection of x onto L is equal to what? It's equal to x dot v, right? Where v is kind of the defining vector for our line. So it's equal to x, which is 2, 3, dot v, which is 2, 1, 2, 1, all of that over v dot v. So all of that over 2, 1, dot 2, 1 times our original defining vector v. So what's our original defining vector? It's this one right here, 2, 1. So times the vector 2, 1. And what does this equal? See, when you take these two dotted each other, you have 2 times 2 plus 3 times 1. So 4 plus 3, so you get 7. This all simplified to 7. And then this you get 2 times 2 plus 1 times 1. So 4 plus 1 is 5. So you get 7/5. That all simplified to 5. That was a very fast simplification. You might have been daunted by this kind of strange looking expression. But when you take dot products, they actually tend to simplify quite very quickly. And then you just multiply that times your defining vector for the line. So we're scaling it up by a factor of 7/5. So multiply it times the vector 2, 1. And what do you get? You get the vector, we do it in a new color. You get the vector 14 over 5 and the vector 7 over 5. And just so we can visualize this or plot it a little better, let me write it as decimals. 14 over 5 is 2 and 4/5, which is 2.8. And this is 1 and 2/5, which is 1.4. And so the projection of x onto L is 2.8, 1.4. So let's see, 1, 2, 2.8 is right about there. And I go 1.4 is right about there. So the vector is going to be right about there. And I haven't even drawn this too precisely, but you get the idea. This is the projection. Our computation shows us that this is the projection of x onto L. And if we draw a perpendicular right there, we see that it's consistent with our idea of this being the shadow of x onto our line L. Well, now we actually can calculate projections. In the next video, I'll actually show you how to figure out a matrix representation for this, what's essentially a transformation. In the last video, we saw.
Oke, itu tadi dijelasin ya projection. Kalau di projection tadi kayak yang vektornya tadi yang dihasilin dari satu vektor yang dipecahkan jadi 2 vektor kayak gitu ya. Terus satunya lagi yang vektor yang tegak lurus tadi sama vektor yang sejajar dengan vektor yang satunya di gambar yang tadi ya.
Let's say I have.
Okay, kita next. Projection in one dimension subspace.
Many videos ago, we introduced the idea of a projection. And in that case, we dealt more particularly with projections onto lines that went through the origin. So if we had some line, let's say L, and let's say L is equal to the span of some vector v, or you could say, alternately, you could say that L is equal to the set of all multiples of v, such that the scalar factors are just any real numbers. These are both representations of lines that go through the origin. We defined a projection of any vector onto that line. And let me just draw it real fast. So let me see. We draw some axes. So if that is my, I want to draw it a little straighter than that. If that is my vertical axis and that is my horizontal axis, just like that. And let's say I have some line that goes through the origin. Let's say, and that doesn't go through the origin. Let's say that that line right there goes through the origin. So that is L. We knew visually that a projection of some vector L onto L, some vector X onto L, so let's say that that is a vector X. Visually, it's essentially if you were to draw, if you have some light coming straight down, it would be the shadow of X onto L. So this right here, that right there, was the projection onto the line L of the vector x. And we defined it more formally. We kind of took a perpendicular. We said that x minus the projection of x onto L is perpendicular to the line L, or perpendicular to everything, or orthogonal to everything on the line L. But this is how at least I visualize it. It's kind of the shadow as you go down onto the line L. And this was a special case in general of projections. You might notice that L is going to be a valid subspace. You could prove it to yourself. It contains the 0 vector. It goes through the origin. It's closed under addition. Any member of it plus any other member of it is going to be another member of it. And it's closed under scalar multiplication. You can take any member of it and scale it up or down. It's still going to be an L. So this was a subspace when we defined this. And just as a bit of a reminder of what it was, we were able to figure out what this projection is for some line L. If you have some spanning vector, the projection onto this line L that goes in through the origin of the vector x, we figured out it was x dot your spanning vector for your line, so x dot v over v dot v, which is really just the length of v squared. So all of this was a number, and then you want it to be in the same direction as your line. It's going to be another vector in your line, so it's going to be times the vector v. So it's just going to be a scaled up or a scaled down version of your spanning vector. Maybe your spanning vector is like that. And really any vector in your line could be a spanning vector, any vector other than the 0 vector. Now, that was a projection onto a line, which was a special kind of subspace. But now we're going to broaden our definition of a projection to any subspace. So we already know that if, let me draw a little dividing line to show that we're doing something slightly different. We already know that if V is a subspace, of Rn, then V complement is also a subspace of Rn. So the orthogonal complement of V, also a subspace. And let's say we have some members, or let me write it this way. Then if we have these two subspaces, you have a subspace and you have its orthogonal complement, we already learned that if you have any member of Rn, so let's say that x is a member of Rn, then x can be represented as the sum of a member of V and a member of the orthogonal complement of V, where, let me write this, where the vector v is a member of the subspace V, and the vector w is a member of the orthogonal complement of the subspace V. Just like that. We saw this several videos ago. We proved that this was true for any member of Rn. Now, given that, we can define the projection of x onto the subspace V as being equal to just the part of x. You can kind of view it, these are two orthogonal parts of x. We define the projection onto V as the part of x that came from V. It's equal to just that vector V. Alternately, you could say that the projection of x onto the orthogonal complement of, sorry, I wrote transpose, onto the orthogonal complement of V is going to be equal to W. So this piece right here is a projection onto the subspace V. This piece right here is a projection onto the orthogonal complement of the subspace V. Now, what I want to do in this video is show you that these two definitions, that this definition right here, when it's in conjunction with this right here, this is equivalent to what we learned up here if the subspace V that we're dealing with, is a line. And, because this was a valid subspace. But not all subspaces are going to be lines. And to see this, we can revisit an example that we saw several videos ago. We had this matrix here, this 2 by 2 matrix, and then we had this other vector B that was a member of the column space of A. And we did this problem to show you that the shortest solution to this right here, was a unique member of the row space. Hopefully that gets your memory on track for when this problem when we first did it. But let me graph it and show you that the solution to that problem, we could have just as easily taken a projection onto a subspace. So let me graph everything in this problem. This might help you remember also about the problem. So let me draw my axes just like that. So the first thing we learned, you could solve this, but I already did this in a video. I think it was 2 or 3 videos ago. The null space of A, or all of the x's that satisfy AX is equal to 0, is a span of the vector 2, 3. So you go 2 to the right, 1, 2, and then you go a 3 up, 1, 2, 3. And so it's the span of this vector. And so the span of that vector is just all of the points. Well, that vector specifies that point, but if you scale this vector up and down, you're going to specify all of the points on this line. All of the points on that line. Let me draw it like that. That's good enough. It shouldn't curve down like that at the end, so let me draw it a little straighter. So this is the null space. That is our null space of that matrix right there. And then the row space was a span of the vector 3 minus 2. You see that right here. 3 minus 2 is the first row. This guy is just a multiple of that one. That's why we don't have this guy right here in the span as well. And if we were to graph it, 3 minus 2, you go out 3, and then you go down 1, 2. It would be the span of this vector right there. Let me draw it like that. And you take all of the scalar multiples of that vector, you're going to specify, and you put those vectors in standard position. They're going to specify, or their tips are going to be on points along this line right there. Along that line right there. I'm trying to make sure I draw them orthogonally. So this right here is the row space. That right there is the row space of A, which is the same thing as the column space of A transpose. And we know that these guys are each other's orthogonal complements. We know, we've seen this in multiple videos, that the null space of A is the orthogonal complement of the row space. And we also know that the orthogonal complement of the null space is equal to the row space. Everything in this is orthogonal to everything in that. Everything in that is orthogonal to everything in this. And you could see it here in this graph, that these two spaces, which are represented by these lines that go through the origin, are orthogonal. And it makes sense that any, we said at the beginning of the video that anything in R2 in this situation, so this is R2, that R2 can be represented as some sum of a unique member of our row space and a unique member of its orthogonal complement. Let's say I have that point right there. How could I represent it as a sum of a member of this and a member of that? Well, if I go along this guy, I have this vector right here. I have that vector right there along that line. And then I have this vector right here. This vector right here. If I were to shift it, this is just drawn in standard position, but I can draw a vector wherever I want. These lines are just all of the vectors drawn in standard position with their tails at the origin. But we learned in I think the first or second vector videos that I can draw them wherever I want. So if I add this vector and that vector, I can shift this vector over, and this vector will be right there. And there you have it. I took an arbitrary point in R2, and I can represent it as a sum of a member of my row space and a member of the row space's orthogonal complement, or the null space. But just to review what we originally did in that problem is we looked at the solution set of this. And we said the solution set of this looks like this. It has a particular solution plus members of your null space plus homogeneous solutions. We've seen that multiple videos ago. So 3, 0, it looks like this, plus members of the null space. So your solution set is going to be parallel to this, but shifted to the right by 3. So it looks, let me draw a little neater than that. And no, let me draw it like that, and then it goes down like, no, the second part I didn't draw it. There you go. Oh, that's not good either. Maybe I'm being too picky. Okay, so this is your solution set. This is your solution. This is your solution set. And if you remember in that video, we said, hey, there's some member of this solution set that is also a member of our row space. And that member of the solution set that is a member of our row space is going to be the shortest solution. And we saw that. You can see it visually right here. Right? This vector right here, it is in our row space. It is a member of our row space. And it also specifies a point on our solution set. And you can see visually that it's going to be the shortest solution. And one way you could think about it is, this is the projection, any solution to, let me pick a good, different, new color, any solution on our solution set, let me see, it's right there. Let's say that is some arbitrary solution on our solution set, right? That's going to be a point in R2, and any point in R2 can be represented as a sum of some vector in our row space and some vector in our null space. And so if I have this vector right here, how could I do that? Well, I could represent it as a sum of this guy right here, and then this vector right here, that vector right here. And this vector right here is clearly a member of my null space. I just shifted over. This line is only when I draw it in standard position. This vector right here, I'm just showing it heads to tails. If I add this member of my row space to this member of my null space, I get an arbitrary solution to my solution set. And if you think about it, the projection of my arbitrary solution onto my row space will be this guy right here. And that just comes from our well, there's two ways to think about it. We could say that, let's say that this is a solution right here. We could say our solution right here is equal to some member of my row space plus some member of my null space. This is the row space, and that is the null space. And so by the definition of a projection onto a subspace I just gave you, we know that the projection of this solution onto my, let me write it a little bit, the projection onto my row space of my solution is just equal to this first thing. It's equal to the component of it that's in my row space. Its other component, we could call it, is in the orthogonal complement of my row space, or it's in my null space. So this is just going to be equal to the R vector. Now, I want to show you that that is essentially equal to the definition that we did before. That this is completely identical to the definition of a projection onto a line, because in this case, the subspace is a line. So let's find a solution set, and the easiest solution that we could find is if we set c is equal to 0 here, we know that x equals 3, 0 is one of the solutions. So x equals 3, 0 looks like that. So we know x equals 3, 0 is a solution. And what we want to do is we want to find this shortest solution, or we want to find the projection of x onto the row space. Or if we wanted, we could also think of it as a projection of x onto this line. This line is equal to the row space. So let's do that. And I'm doing this to show you that this definition of a projection onto a subspace that I've just introduced you to in this video, it is completely identical to the definition, or it's not identical. It's consistent with the definition of a projection onto a line, although this is more general because a subspace doesn't have to be a line. But in this case, it is a line. So let's do that. So the projection of 3, 0, the projection of the vector 3, 0 onto our row space, which is a line, so we can use that formula, it is equal to 3, 0 dot the spanning vector for our row space, right? dot the spanning vector for our row space. That was 3 minus 2. We could have, there's a bunch of spanning vectors for your row space. This is just the one we happen to pick. So dot 3 minus 2 all over the spanning vector dotted with itself, 3 minus 2 dot 3 minus 2. And then this is just going to be one big scalar, and then we want to multiply that, or essentially scale up our actual spanning vector by that. So this is the projection of this solution onto my row space, which should give me this vector right here, because we're just taking a projection onto a line, because the row space in this subspace is a line. And so we used the linear projections that we first got introduced to, I think, when I first started doing linear transformations. So what is 3? So let's see, this is 3 times 3, 3 times 3, plus 0 times minus 2. 0 times minus 2. This right here is equal to 9. This is 3 times 3 plus, let's see, this is 3 times 3 plus minus 2 times minus 2. So that's 9 plus 4. That's 13. So it's 9 over 13 times this vector right here. So we're going to get, it's going to be equal to 9 over 13 times the vector 3 minus 2, which is equal to the vector 27 over 13 and then minus 18 over 13, which is this vector right here. Which is this vector right here. Which we got this exact answer when we first did it, although we just didn't use the projection onto a line. But now we see that this is exactly consistent with what we did before. We just used the projection onto a line. And we see that this is consistent with our new, broader definition of a projection. Our new, broader definition of a projection. Here we were able to do it because we did it onto a line. But here I'm calling a projection onto any subspace. We know how to do it if it's a line, but so far I've just kind of defined it onto an arbitrary subspace. But I haven't given you a nice mathematical, I guess, or computational way to figure out what this is going to be if this isn't a line. In fact, I haven't even showed you, when this is general, whether this is definitely a linear transformation. We know that when you take the projection onto a line, it's a linear transformation, but I haven't shown you that when we take a projection onto an arbitrary subspace, that it is a linear projection. I'll do that in the next video.
Oke, itu untuk yang tadi projection one dimension in subspace. Kita lihat contoh projection into one dimension.
In the last video, we derived the formula for projections of vectors onto a one-dimensional subspace. In particular, we arrived at this equation if we choose the dot product as the inner product. Here, x is a d-dimensional vector, and b is the basis vector that spans that one-dimensional subspace that we want to project x onto. In this video, we're going to look at an example. Assume our vector b that spans our one-dimensional subspace is the vector 2, 1, and the vector x we want to project onto that subspace is given by 1, 2. Let's quickly draw this. So x is the vector 1, 2. So x is living over here. And the vector b is going to be the vector 2, 1. And so this is b. And b spanning our subspace means that our subspace U is going to extend along this line. So now we're interested in computing the orthogonal projection of x onto U. So using now this equation here, we get, so x transpose times b is 2 plus 2. And now we divide by the squared norm of b. So the length of b is 2 squared plus 1 squared square root. So overall, we get the squared norm to be 5. And then times b will get us to 2, 1. So overall, 4 over 5 times the vector 2, 1. This means that our orthogonal projection is 4 over 5 times the vector b. That means if we take 4/5 of this vector, then we will get to our orthogonal projection. So this point here is now pi u of x, so the orthogonal projection of x onto u. And the length of this segment is 4/5 times the length of b. We've gone through orthogonal projections onto one-dimensional subspaces. In the next video, we're going to look at orthogonal projections onto high-dimensional subspaces.
Oke, itu contohnya kalau untuk yang playlist tadi aku sempat kirim di chat itu nanti full kayak gini nih. Jadi emang yang dari Imperial College London gitu. Itu bisa banget buat ditonton satu-satu, kayaknya per video nggak sampai 10 menit.
Hi, I'm Mark. I'm a lecturer in statistical machine learning at Imperial College. In this course, we were going through the mathematical foundations that we need in order to do dimensionality reduction with principal component analysis. Data in real life is often high dimensional. For example, if we want to estimate the price of our house in a year's time, we can use data that helps us to do this. The type of the house, the size, the number of bedrooms and bathrooms, the value of houses in the neighborhood, when they were bought, the distance to the next train station and park, the number of crimes committed in the neighborhood, the economic climate, and so on and so forth. There are many things that influence the house price, and we collect this information in a data set that we can use to estimate the price of our house. Another example is the 640 by 480 pixels color image, which is a data point in a one-dimensional space, where every pixel corresponds to 3 dimensions, one for each color channel, red, green, and blue. Working with high-dimensional data comes with some difficulties. It is hard to analyze, interpretation is difficult, visualization is nearly impossible, and from a practical point of view, storage can be quite expensive. However, high-dimensional data also has some nice properties. For example, high-dimensional data is often overcomplete. That means many dimensions are redundant and can be explained by a combination of other dimensions. For example, if we took a color image with 4 channels, red, green, blue, and a grayscale channel, then the grayscale channel can be explained by a combination of the other 3 channels, and the image could equally be represented by red, green, and blue alone, as we can reconstruct the grayscale channel just using that information. Dimensionality reduction exploits structure and correlation and allows us to work with a more compact representation of the data, ideally without losing information. We can think of dimensionality reduction as a compression technique similar to JPEG or MP3, which are compression algorithms for images and music. Let's take a small binary image of the handwritten digit 8. We're looking at 28 by 28 pixels, each of which can be either black or white. Therefore, this image can be represented as a 784-dimensional vector. However, in this example, the pixels are not randomly black or white, they're structure. They often have the same value as the neighboring pixels. In this dataset, there are many examples of an 8. They differ a little bit, but they look sufficiently similar that we can identify them as 8. We can use dimensionality reduction now to find a lower dimensional representation of all 8s that is easier to work with than a 784-dimensional vector. The lower dimensional representation of a high dimensional data point is often called a feature or a code. In this course, we will look at a classical algorithm for linear dimensionality reduction, principal component analysis, or PCA. The purpose of this course is to go through the necessary mathematical details to derive PCA. In the first module, we will look at statistical representations of data, for example using means and variances. And we also describe how means and variances change if we linearly transform our dataset. In the second module, we will look at the geometry in vector spaces and define how to compute distances and angles between vectors. In the third module, we'll use these results to project data onto lower dimensional subspaces, and in the fourth module, we'll derive PCA as a way to reduce dimensionality of data using orthogonal projections.
Oke, itu tadi sedikit penjelasan tentang course-nya. Untuk yang ini, kita lanjut lagi.
Pengumuman pada seluruh pelajar.
In the last video, we derived the formula for projections of vectors onto a one-dimensional subspace. In particular, we arrived at this equation if we choose the dot product as the inner product. Here, x is a d-dimensional vector, and b is the basis vector that spans that one-dimensional subspace that we want to project x onto. In this video, we're going to look at an example. Assume our vector b that spans our one-dimensional subspace is the vector 2, 1, and the vector x we want to project onto that subspace is given by 1, 2. Let's quickly draw this. So x is the vector 1, 2. So x is living over here. And the vector b is going to be the vector 2, 1. And so this is b. And b spanning our subspace means that our subspace U is going to extend along this line. So now we're interested in computing the orthogonal projection of x onto U. So using now this equation here, we get, so x transpose times b is 2 plus 2. And now we divide by the squared norm of b. So the length of b is 2 squared plus 1 squared square root. So overall, we get the squared norm to be 5. And then times b will get us to 2, 1. So overall, 4 over 5 times the vector 2, 1. This means that our orthogonal projection is 4 over 5 times the vector b. That means if we take 4/5 of this vector, then we will get to our orthogonal projection. So this point here is now pi u of x, so the orthogonal projection of x onto u. And the length of this segment is 4/5 times the length of b. We've gone through orthogonal projections onto one-dimensional subspaces. In the next video, we're going to look at orthogonal projections onto high-dimensional subspaces.
Kita lanjut lagi. Next video tadi yang n-dimensional projection.
In the last video, we learned about orthogonal projections onto one-dimensional subspaces. In this video, we look at the general case of orthogonal projections onto n-dimensional subspaces. For this, we'll exploit the same concepts that worked in the one-dimensional case. Let's start with an illustration. We're going to look at a case where we have a vector x that is living in a three-dimensional space, and we define a subspace, a two-dimensional subspace U, which has basis vectors b1 and b2, which are, for example, this vector, and b2 is this vector. So we write U is spanned by b1 and b2. So U in this case would be the plane down here. So this is U. So now we are looking at the orthogonal projection of x onto U, and we're going to denote this by pi u of x. So that projection is going to look something like this. That's the projection point. So this is the orthogonal projection of x onto the subspace U. So we can already make two observations. The first thing is that because pi u of x is an element of U, it can be represented as a linear combination of the basis vectors of U. So that means we can write pi u of x is lambda 1 times b1 plus lambda 2 times b2 for appropriate values of lambda 1 and lambda 2. And the second property is that the difference vector of x minus pi u of x, so this vector over here, is orthogonal to U, which means it's orthogonal to all basis vectors of U. And we can now use the inner product for this, and we can write that x minus pi u of x inner product with b1 must be 0, and the same is true for b2. But now let's formulate our intuition for the general case where x is a d-dimensional vector and we're going to look at an m-dimensional subspace U. Okay, let's derive this result. I copied our two insights up here and I have defined two quantities. A lambda vector which consists of all these lambda I here, and a B matrix where we just concatenate all basis vectors of our subspace U. Now, with this definition, we can also write pi u of x equals b times lambda. Let's assume we use the dot product as our inner product. Now, if we use our second property, we'll get that so pi u of x minus x inner product with bi is now equivalently written as the inner product of b lambda minus x and bi, and this needs to be 0, where I just used the definition of p u of x in here. So now we can simplify this by exploiting the linearity of the inner product, and we'll get b lambda times, or inner product with bi minus the inner product of x with bi needs to be 0. And this holds for I equals 1 to m. With the inner product, we can now write this in the following way. We can write this as lambda transpose times b transpose times bi minus x transpose times bi equals 0 for I equals 1 to m. And now we can write this as a set of conditions. And if we summarize this, we would get lambda transpose times b transpose times b minus x transpose times b must be 0. Now we need to talk here about an m-dimensional 0 vector. What we would like to do now is we would like to identify lambda. For this, we are going to right multiply the inverse of b transpose times b onto the entire equation. And then we get lambda transpose equals x transpose times b times b transpose b inverse, which then also means we can write lambda as the transpose of this entire expression. We get b transpose b inverse, so this matrix is symmetric, so its transpose is the same as the original matrix, times b transpose x. So now we have identified lambda to be this, but we also know that our projection point can be written as b times lambda. So this means we will get pi u of x as b times lambda, which is b times b transpose b inverse times b transpose x. We can now identify this expression as the projection matrix, similar to the one-dimensional case. And in the special case of an orthonormal basis, b transpose times b is the identity matrix. So we would get pi u of x is b times b transpose times x. The projected vector pi u of x is still a vector in Rd, but we only require m coordinates, the lambda vector over here, to represent it as a linear combination of the basis vectors of the subspace U. We also effectively got the same result as in the one-dimensional case. Remember, in 1D we got lambda equals b transpose x divided by b transpose b, and we got a projection point pi u of x, which was b transpose x divided by b transpose b times b. Now, b transpose b is now expressed as matrix b transpose times matrix b, but we now have the inverse matrix sitting here instead of dividing by a scalar. That's the only difference between these two results. In this video, we looked at orthogonal projections of a vector onto a subspace of dimension m. We arrived at the solution by exploiting two properties. We must be able to represent the projection using a linear combination of the bases of the subspace, and the difference vector between the original vector and its projection is orthogonal to the subspace. In the next video, we're going to look at a concrete example.
Oke. Sampel untuk yang n-dimensional. Oke, kita lanjut. Projection subspace is a linear transformation. Kemarin kita sempat bahas juga ya yang linear transformation di hari pertama.
We've defined the notion of a projection onto a subspace, but I haven't shown you yet that it's definitely a linear transformation, nor have I shown you that if you know a basis for its subspace, how do you actually find the projection onto it? So let's see if we can make any progress on that here. So let's say I have some subspace. Let's say V is a subspace of Rn. And let's say I've got some basis vectors for V. So let's say these are my basis vectors. Basis vector 1, 2, 2, and I have k of them. I don't know what V's dimension is, but let's say it's k. It's got k basis vectors. So is a basis for V, and that means that any vector, not V, that's not V vector, that's V subspace. Now that means that any vector, let me call some vector, I don't know, let's say any vector A that is a member of my subspace can be represented. That means that A can be represented as a linear combination of these guys. So I'll make my linear combination, let's say it is, I don't know, y1 times b1 plus y2 times b2 all the way to plus yk times bk. That's what the definition of a basis is. The span of these guys is your subspace V, so any member of V can be represented as a linear combination of my basis vectors. Now, if I were to construct a matrix, let's make it an n by k matrix, whose columns are essentially the basis vectors of my subspace. So A looks like this. The first column is my first basis vector. My second column is my second basis vector. And I go all the way to my kth column, and I have k columns, is going to be my kth basis vector. If I'm going to have my kth basis vector, let me make the closing bracket the same color as my opening bracket. Just like that, it's going to have n rows because each of these basis vectors are members of Rn. Remember, V is a subspace of Rn, so each of these guys are going to have n terms. So this matrix is going to have n rows. Now, saying that any member of the subspace V can be represented as a linear combination of these basis vectors is equivalent to saying that any member A of our subspace V can be represented as the product of our matrix A times some vector y, where something was equal to A, for some y that is a member of Rk. Now, why is this statement and that statement equivalent? Well, you can imagine if you were to just multiply this times some vector y in Rk, so it's y1, y2, all the way down to yk, this is going to be equal to y1 times b1 plus y2 times b2, all the way to plus yk times bk, which is the same thing as this. So if you can always pick the right linear combination, you can always pick the right member of yk, so that you get the right linear combination of your basis vectors to get any member of your subspace V. So any member of my subspace right there can be represented as the product of the matrix A with some vector in Rk. And we don't know much about this vector right here in Rk. Now, the projection, let's say that x is just some arbitrary member of Rn. The projection of x onto our subspace V, that is, by definition, it is going to be a member of your subspace. Or, another way of saying it is that this guy, the projection onto V of x, is going to be equal to, my matrix A is going to be equal to, I'll do it in blue, is going to be equal to A times some vector y, for some vector y in Rk. If we knew what that vector y was, if we could always find it, then we would have a formula, so to speak, for figuring out the projection of x onto V. But we don't have that yet. All I've said is any member of V can be represented as a product of our matrix A, which has the basis for V as columns, and some member of Rk. That just comes out of the fact that these guys span V, that any member of V is a linear combination of those guys. We know that the projection of x onto V is a member of our subspace V. It has to be inside of V. So it can also be represented this way. Now, what was our definition of our projection? our definition of our projection, we say, well, let me write it this way. We know that x can be represented as the sum of the projection onto V of x plus some member of V complement. Or maybe I could even write plus the projection onto the orthogonal complement of V. Onto the projection of x onto the orthogonal complement of V. You could write it this way. I could have also written this as W, where W is a member of V complement. Actually, let me write it that way. That might make it simpler. I don't want to write too many projections here. Plus W, where W is a unique member of the orthogonal complement of V. Or you could say it this way. If you subtract the projection of x onto V from both sides, you get x minus the projection of x onto V is equal to W. Or another way to say it is that this guy right here is going to be a member of the orthogonal complement of V, right? Because this is the same thing as W. Now, what's the orthogonal complement of V? If we go back to this matrix here, I have V's basis vectors right here as the columns. So the column space of A is going to be equal to V, right? The column space of A is just the span of these basis vectors, and by definition, that is going to be equal to my subspace V. Now, what is the orthogonal complement of V? The orthogonal complement of V is going to be the orthogonal complement of my column space. And what's the orthogonal complement of a column space? That's equal to the null space of A transpose. Or you could also call that the left null space of A. But that we've seen that many, many videos ago. So we could say that x minus the projection of x onto V is a member of, let me write it this way, x minus the projection onto V of x is a member of the orthogonal complement of my column space of my matrix, which is equal to the null space of A transpose. That's the orthogonal complement of V. This is the same thing as the orthogonal complement of V. But what does this mean? What does this mean right here? This means that if I take A transpose and I multiply it times this vector, because it's a member of A transpose's null space. So if I multiply it times that vector right there, so projection of x onto V, that I'm going to get 0. I'm going to get the 0 vector. That's the definition of a null space. So let's write this out a little bit more. Let's see if we can algebraically manipulate it a bit. So if we distribute this matrix vector product, we get A transpose times the vector x minus A transpose times the projection. Actually, let me write this way. Instead of keep writing the projection onto V of x, what did we say earlier in this video? We said that the projection of V onto x can be represented as the matrix product of the matrix A times some vector y in Rk. That's where we started off the video. So let me write it that way, because that's going to simplify our work a little bit. So I'm going to distribute the A transpose times x, and then A transpose minus A transpose times this thing. This thing I can write as A times some vector y. And that was this is just a byproduct of the notion that the projection is a member of our subspace. Because it's a member of our subspace, it's going to be some linear combination of the column vectors of A. We saw that up here, so it can be represented in this way. So instead of projection onto V of x, I can just write A y. This thing and this thing are equivalent because this thing is a member of V. And then all of that is going to be equal to 0. And then if we add this to both sides of this equation, we get that A transpose x is equal to A transpose A of y. Or, now this is interesting. Now remember where we started off here. We said that the projection onto v of x is equal to ay for some y that is a member of Rk. If we knew what that y was, if we could always solve for that y, then the projection of x would be well defined, and we could always just figure it out. Now, can we solve for y here? Well, we'll be able to solve for y if we can take the inverse of that matrix. If this matrix is always invertible, then we're always going to be able to solve for y here, because we can just take the inverse of this matrix and multiply it times the left side of both sides of this equation. Now, if you remember, 3 videos ago, I think it was 3 videos ago, I showed you that if I have a matrix A whose columns are linearly independent, then A transpose A is always invertible. The whole reason why I did that video is for this moment right here. Now, what about our matrix A? Well, our matrix A has column vectors that form the basis for a subspace. By definition, basis vectors are linearly independent. So our matrix A has columns that are linearly independent. And if you watched that video and if you believed what I told you, then you know that A transpose A, in our case, is going to be invertible. It has to be invertible. So let's take the inverse of it and multiply it times both sides. So if we take A transpose A inverse, we know that this exists because A has linearly independent columns. And multiply it times this side right here, A transpose X. And then on this side, we're going to do the same thing. A transpose A inverse times this thing right here, A transpose A y. These two things, when you multiply the inverse of a matrix times a matrix, you're just going to get the identity matrix. So that's just going to be equal to the identity matrix. And the identity matrix times y is just going to be y. So we get, and this is a vector, so if I flip them around, I get that y is equal to this expression right here. A transpose A inverse, which will always exist, times A transpose times x. Now, we said that the projection of x onto v is going to be equal to a times y for some y. Well, we just solved for the y using our definition of our projection. We just were able to solve for a y. So now we can define our projection of x onto v as a matrix vector product. So we can write the projection onto v of our vector x is equal to a times y, and y is just equal to that thing right there. Y is equal to that thing right there. So A times A transpose A inverse, which always exists because A has linearly independent columns, times A transpose times x. And this thing right here, this long convoluted thing, that's just some matrix. Some matrix which always exists for any subspace that has some basis. So we've just been able to express the projection of x onto a subspace as a matrix vector product. So this says, so anything that can be any matrix vector product transformation is a linear transformation. And not only did we show that it's a linear transformation, we showed that, look, if you can give me the basis, for v, I'm going to throw that basis into I'm going to make those column vectors equal to the column of some matrix A. And then if I take matrix A, if I take its transpose, if I take A transpose times A and invert it, and if I multiply them all out in this way, I'm going to get the transformation matrix for the projection. Now, this might seem really complicated, and it is hard to do by hand for many, many projections, but this is super useful if you're going to do some three-dimensional graphical programming. If you have, let's say you have something in, you have these cubes, let's say you have some, three-dimensional object. Let's say you have some three-dimensional object, and you want to know what it looks like from the point of view of some observer. So let's say you have some observer. Some observer's point of view is essentially going to be some subspace, right? You want to see what the projection of this cube onto the subspace. How would it look to the person who's essentially onto this flat screen right there? How would that cube look from this point of view? Well, if you know the basis for this subspace, you can just apply this transformation. You can, make a matrix with whose columns are these basis vectors for this observer's point of view. And then you can apply this to every vector in this cube in R3, and you will know exactly how this cube should look from this person's point of view. So this is actually a super useful result.
Oke.
I got this.
Itu tadi penjelasannya projection yang di linear transformation. Terus ini subspace projection matrix example.
Let's say I've got some subspace V, which tends to be our favorite letter for subspaces, and it's equal to the span of two vectors in R4. Let's say that the first vector is 1, 0, 0, 1, and the second vector is 0, 1, 0, 1. That is my subspace V. And you can see that these are going to be a basis, that these are linearly independent, right? Two vectors that are linear, or any a set of vectors that are linearly independent and that span a subspace are a basis for that subspace. And you can see they're linearly independent. This guy has a 1 here. There's no way that you can take some combination of this guy to somehow get a 1 there. And then this guy has a 1 here. There's no way you can get some linear combination of these zeros here to get a 1 there. So they're linearly independent. So you could also call this a basis. A basis for V. Now, given that, let's see if we can find out the transformation matrix for the projection of any arbitrary vector onto this subspace. So let's say that x, we're dealing in R4 here, right? So let's say that x is a member of R4, and I want to figure out what the projection, I want to figure out a transformation matrix for the projection onto V of x. Now, in the last video, we came up with a general way to figure this out. We said if A is a transformation matrix, if A is a matrix whose columns are the basis for the subspace. So let's say A is equal to 1, 0, 0, 1, 0, 1, 0, 1. So A is a matrix whose columns are the basis for a subspace. Then the projection of x onto V would be equal to, and this is kind of hard, the first time you look at it, it gives you a headache, but there's a certain pattern to, or a symmetry, or a way of, you could say it's A times, you're going to have something in the middle, and then you have A transpose times your vector x. And the way I remember it is, in the middle you have these two guys switched around, so then you have A transpose A, and you take the inverse of it. So, you probably won't be using this in your everyday life 5 or 10 years from now, so it's okay if you don't memorize it, but temporarily put this in your medium-term memory because it's a good thing to know, for doing these projection problems. So if we want to find the general matrix for this transformation, we just have to determine what this matrix is equal to. And that's just a bunch of matrix operations. So that's A. What is A transpose? A transpose is going to be equal to just all the rows turned to columns. So the first column becomes the first row. So it becomes 1, 0, 0, 1. Second column becomes the second row. 0, 1, 0, 1. That's what A transpose is. Now what's A transpose A? To figure out that, I want to figure out what A transpose times A is. So let me multiply A transpose times A. So I'll rewrite A right here. 1, 0, 0, 1, 0, 1, 0, 1. This is give us some good practice on matrix products. This is going to be equal to what? Well, first of all, we have this is a 2 by 4 matrix, and I'm multiplying it by a 4 by 2 matrix. So it's going to be a 2 by 2 matrix. So the first entry is essentially the dot product of that row with that column. So it's 1 times 1 plus 0 times 0 plus 0 times 0 plus 1 times 1. So it's just going to be 2 for that first entry right there. And then you take the dot product of this guy with this guy right here. So it's 1 times 0, which is 0, plus 0 times 1, which is 0, plus 0 times 0, which is 0, plus 1 times 1, which is 1. Now we do this guy. This guy dotted with this column right there. 0 times 1 is 0, plus 1 times 0 is 0, plus 0 times 0 is 0, plus 1 times 1 is 1. And then finally, this row dotted with this second column. Second row at second column. 0 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. 1 times 1 is 1. So we have 1 times 1 plus 1 times 1. So it's going to be 2. It's going to be equal to 2. So this right here, that right there is A transpose A. But that's not good enough. We need to figure out what the inverse of A transpose A is. This is A transpose A, but we need to figure out A transpose A inverse. So what's the inverse of this? So let me write it here. The inverse, A transpose A inverse, is going to be equal to what? It's 1 over the determinant of this guy. And what's the determinant here? It's going to be 1 over the determinant of this. The determinant is 2 times 2, which is 4, minus 1 times 1. So it's 4 minus 1, which is 3. So 1 over the determinant times this guy, where if I swap these two, so I swap the ones, I swap the 2's. So this 2 goes here, and then this orange 2 goes over here. And then I make these 1's negative. So this becomes a minus 1, and this becomes a minus 1. We learned that this is a general solution for the inverse of a 2 by 2 matrix. I think it was 10 or 11 videos ago, and you probably learned this in your Algebra 2 class, frankly. But there you go. We have A transpose A inverse. So we have this guy. We have this whole guy here is just this matrix. I could multiply the 1/3 into it, but I don't have to do that just yet. But let's figure out the whole matrix now. The whole A times this guy, A transpose A inverse, times A transpose. So let me write it this way. So the projection onto the subspace V of X is going to be equal to A. Is going to be equal to A 1 0 0 1 0. Let me do a little bit. Let me write it a little bit bigger like this. So 1 0 0 1 0 1 0 1 times A transpose A inverse, right? A times A transpose A inverse, which is this guy right here. And let's just put the 1/3 out front, just because that's just a scalar. So I'll put the 1/3 out front times this guy. This A transpose A inverse is 1/3 times 2 minus 1 minus 1, 2. And then I'm going to multiply it times A transpose. Times A transpose. And then all of that times our vector x. So A transpose is right there. A transpose is right there. It is 1 0 0 1 0 1 0 1. And then all of that's going to be times your vector x. So we still have some nice matrix products ahead of us. Let's see if we can do these. So the first one, let's just multiply these two guys. Let's multiply those two guys. I don't think there's any simple way to do it. So we have, this is a 2 by 2 matrix, and this is a 2 by 4 matrix. So when I multiply them, I'm going to end up with a 2 by 4 matrix. So let me write that 2 by 4 matrix right here. And then I can write this guy right here. 1 0 0 1 0 1 0 1. And then I have the 1/3 that was from A transpose A inverse, but I put the scaling factor out there. And all of this is equal to the projection of x onto v. So let's do this product. So this first entry is going to be 2 times 1 plus minus 1 times 0. So that is just 2. Then you're going to have 2 times 0 plus minus 1 times 1. Well, that's minus 1. Then you're going to have 2 times 0 plus minus 1 times 0. Well, that's just 0. And then you're going to have 2 times 1. 2 times 1 plus minus 1 times 1. That's 2 minus 1. That's just 1, right? 2 times 1 plus minus 1 times 1. Fair enough. Now let's do the second row. Minus 1 times 1 plus 2 times 0. So that's just minus 1. Minus 1 times 0 plus 2 times 1. Well, that's just 2. Minus 1 times 0 plus 2 times 0. That's just 0. Minus 1 times 1 plus 2 times 1. Well, that's minus 1 plus 2. So that is 1. Almost there. And of course, we have to multiply it times x at the end. That's what the transformation is. But this right here is our transformation matrix. One more left to do. Let's hope I haven't made any careless mistakes and that I won't make any when I'm doing this product. Because this is going to be a little more complicated because this is a 4 by 2 times a 2 by 4. I'm going to end up with a 4 by 4 matrix. So let me give myself some breathing room here because I'm going to generate a 4 by 4 matrix right there. And so what am I going to get? So this first entry is going to be 1 times 2 plus 0 times minus 1. So it's just going to be equal to 2. The next entry, 1 times, this column times, this row times any column here is just going to be the first entry in the column, right? Because it gets zeroed out. So 1 times 2 plus 0 times minus 1 is just 2. 1 times minus 1 plus 0 times 2 is just minus 1. 1 times 0 plus 0 times 0 is 0. 1 times 1 plus 0 times 1 is just 1. Right? When you take this row and you multiply it times these columns, you literally just got your first row there. Now let's do this. Let's do this row times these columns. Now you got a 0 here, so you're going to have a 0 times the first entry of all of these and a 1 times the second one. So 0 times 2 plus 1 times minus 1 is minus 1. 0 times minus 1 plus 1 times 2 is 2. You're just going to get the second row here. 2, 0, 1. And that actually makes sense because if you just look at this part of the matrix, it's the 2 by 2 identity matrix. So anyway, that's a little hint why this looks very much like that. But we're just going to go through this matrix product. Now you multiply this. Let me do it in a different color. You multiply this guy times each of these columns. That guy dotted with that is just going to be 0 because this guy is essentially the 0 row vector. So you're just going to get a bunch of zeros. And then finally, this last row, it's 1 times the first entry plus 1 times the second entry. So this guy is going to be 2 plus minus 1, which is 1. Minus 1 plus 2, which is 1. 0 plus 0, which is 0. And then 1 plus 1, which is 2. And all of that times x. And there you have it. This is exciting. The projection onto V of x is equal to this whole matrix times x. So this thing right here, I could multiply the 1/3 into it, but we don't have to do that. That'll just make it a little bit more messy. This thing right here is the transformation matrix. The transformation matrix. And it's as you can see, since we're transforming, remember this projection, the projection onto V, this is a linear transformation from R4 to R4. You give me some member of R4, and I'll give you another member of R4 that's in my subspace. That is the projection. So this is going to be a 4 by 4 matrix. You can see it right there. Anyway, hopefully you found that useful to actually see a tangible result. R4 is very abstract, so this would even be beyond our three-dimensional programming example. This would be, we're dealing with a more abstract data set where we're interested in finding a projection.
Oke, itu untuk projection. Oke, sekarang kita demo ortogonal. Okay, orthogonal projection. Learning objective, write code that project data onto a lower dimensional subspace. Terus number 2, understand the real-world application of projection. Jadi yang pertama kita selalu import dulu library-nya. Oke, di sini kita pakai Olivetti Face Dataset. Oke, di sini ada advice for testing numerical algorithm. Di sini ada beberapa tips yang akan membantu kita untuk mengidentify bugs dari implementation kita. Yang pertama itu test on small dataset, yang kedua find invariants. Okay, we can find some invariant for projection in the cell below. We have written two function which check for invariance of projection. Ada dua fungsi untuk ngecek invariant yang ada di projection. See in the docstring which explain what each of them docs does. Oke, ini kita running dua-duanya. Yang pertama ada fungsi test property projection matrix. Ini untuk tes apakah projection matrix itu satisfy certain properties. Terus kita harus punya P sama dengan P dan P sama dengan P pangkat T. Terus untuk yang test property projection ini test orthogonality of X and its projection P. Di sini pakai np dot P min X, P. Untuk orthogonal projection, sini ada recall that for projection of a vector X onto a one-dimensional subspace U with basis P, we have ini rumusnya, formulanya. Oke, terus di sini and from the general projection onto an m-dimensional subspace U with basis vektor P1 hingga P ke M. We have ini formulanya ketika B sama dengan P1 hingga P ke M. Ini tugas kita adalah untuk implement orthogonal projection. Jadi kita bisa split tugas ini ke dalam dua step. Yang pertama kita find the projection matrix P that projects any X onto U. Terus yang kedua, the project vector PU X of X can be written as UX sampai X. To perform step 1, you need to complete, kita harus complete fungsi yang ada di bawah ini, fungsi projection matrix. One dimension dan projection matrix general. Terus yang selanjutnya kita complete si projection underscore I, 1 dimension 1D. Terus yang kedua project general. Oke, ini ada fungsi project matrix 1D yang terima parameternya B yang tadi basis ya. Basis vector P itu dia compute the projection matrix onto the space spanned by B. B itu and the array of dimension D and the basis. Jadi B itu basisnya ya. Basis for the subspace. Dia nge-return P projection. Sini lanjut fungsi kedua. To projection 1D, dia terima X sama B. Ini untuk compute the projection matrix onto the space spanned by B. X itu vector to be project, terus yang B itu tadi basisnya, dia akan nge-return Y, projection of X in space spanned by B, B basisnya. Terus lanjut lagi, fungsi ketiga itu projection matrix general B besar di sini. Compute the projection matrix onto the space spanned by B. Oke, di sini dia nge-return projection matrix P besar, sama ini juga project general. Dia compute the projection matrix onto the space spanned by B. B-nya basis. Kalau yang atas basis D, yang bawah ini basis yang B besar pertama itu basis D, M, yang ini D, E. Return Y projection of X in space spanned by B projection matrix. Dipanggil fungsi yang tadi projection matrix general. Sini we have include some unit tests for you to test your implementation. The orthogonal projection in 2 dimension. Define basis vector for subspace. Ini based on NP array 2,1 reshapes min 1,1. Yang kedua point to be in the project letter NP array. Ini X sama dengan NP array 1,2 reshape min 1,1. Oke, di sel selanjutnya kita akan cek that the invariant hold for the function that you have implement earlier. Oke, di sini tes 1 dimensi, NP test assert almost equal, kita panggil tadi projection matrix 1 dimension, terus untuk yang selanjutnya kita panggil project 1D-nya. Terus kita dapat B besar di sini ada, kita masukin B kapital, NP array 10, 11, 12, kita tes. Sini projection matrix general, kita masukinnya B, terus NP general, print correct. It always good practice to create your own test case. Create some test case of your own below. Oke, kita lanjut eigenphase. Ini optional. Next, we will take a look at what happens if we project some dataset consisting of human face onto some basis we call the eigenphase. You don't need to know what eigenphase are for now, but you will know what they are towards the end of the course. Oke. Di sini kita pakai scalar dataset, kita import yang tadi datasetnya fetch Olivetti fetch. Sini juga fetch LFW people, ini kita pakai yang interact, kemarin sempat kita bahas juga yang interact. Terus sini kita load face datanya di dataset Olivetti face. Kita visualisasiin gambarnya. Ini pakai dataset yang kemarin sempat kita lihat juga ya. For numerical reason, we normalize dataset. Kita normalisasiin datasetnya. Oke. Bentar, masih proses. Oke, di sini kita ganti path-nya terlebih dahulu. share drive. Oke. Sebentar, karena datasetnya harus download dulu yang ini data NPY-nya ini. NPY. Oke, kita refresh. Oke, ya NPY, kita copy path-nya. Oke, di sini 250 kita hanya pakai the first 50 dimension aja, dimension of the basis. Kita running. Oke, shape-nya 506464. Oke, each instance in P is 64,64 image. An icon face. Jadi 64 kali 64 image. Terus kita lihat PLT figure, carry shape. Nah ini visualize-nya dari yang tadi icon face yang kita masukin. Nah, di sini take a look at what happen if we project our face onto the basis space spanned by this 50 icon face tadi. In order to do this, we need to reshape P from above, which of size 50,6464. Tadi kita bikin size-nya ya, karena kita cuma ambil 50 yang pertama. Into the same shape as the matrix representing the basis as we have done earlier, which is of size, berarti kan tadi awalnya size 4096 50. Here 4096 is dimensionality of the data and 50 is the number of data points. Then we can reuse the function we implement earlier to compute the projection matrix and the projection. Complete the code below to visualize the reconstructed face that lie on the subspace spanned by an eigenface. Kita pakai yang tadi udah kita buat. Oke, di sini ada yang project general tadi kita pakai. Oke. Ini kita reshape data we load in variable P so that we have a matrix representing the basis. Di sini ya tadi disuruh masukin yang 40.096,50 size. Oke, lanjut least square regression. Okay, consider the case where we have a linear model for predicting housing price. We are predicting the housing price based on features in the housing data set. If we denote the feature as x0 hingga x ke n and collect them into a vector x and the price of the house as y, assuming that we have a prediction model in the way such that y sama dengan fxi sama dengan theta pangkat t xi. Jadi jika kita collect dataset ke dalam n, d data matrix x, kita dapat nulis modelnya kayak gini ya, formula modelnya tadi. Terus ini ada node data points, the row of the data matrix. Every column is dimension of the data. Setiap kolom adalah dimensi datanya. Our goal is to find the best data such that we minimize the following objective. Jadi kita cari the best datanya ya buat minimize following objective tadi yang least square kena. Di sini kalau ini formulanya kalau kita set gradiennya itu above objective to 0, we have jadi kalau kita masukin objektifnya above objective to 0 kayak ini, jadi terus the solution that give zero gradient solve, which we call the maximum likelihood estimator, the following equation. Jadi equationnya ini sama, this is exactly the same as normal equation we have for the projection. This means that if we solve yang kita dapat tadi ini, we solve for, we will find the best data itu pakai formula yang ini. Jadi kita ada fungsi f, itu kita pakai send random seed, so we get the deterministic output. Terus kita returnnya si tadi yang theta dikali kayak formula yang tadi, observation occurred by some noise, so that we don't get x, y on a line. Ini yang tadi maximum likelihood estimator. Yang ini ya. Oke, dia langsung theta head yang ini, yang estimatornya. Kalau theta itu yang atas tadi. Di sini tetanya 2,0000. Theta headnya 1,95 sekian. Okay, what would happen to theta if we increase the number of data point? Kalau kita kurangi number of data point-nya. Kalau kita menambah number of data point-nya. Terus sini make your hypothesis. Kita buat program yang bisa confirm itu. Sini n sama dengan np arrange 2,10.000, stepnya 10. Theta underscore error sama dengan np0 and shape. Plus theta underscore error sama dengan np1 and shape. Oke, ini data setnya. Kalau parameter error. Ini data set size-nya tadi. Oke. Oke. Sampai di sini mungkin ada yang mau tanya. Ini berat banget sih materinya. Nanti boleh diulang-ulang lagi nontonnya, juga boleh nonton yang playlist yang tadi belum kita lihat. Itu boleh banget, karena banyak potongan-potongan video tuh yang dijadiin materi di sini gitu. Oke, kalau belum ada yang mau bertanya, untuk tugas minggu ini itu nanti nggak ada tugas coding, terus untuk kuisnya nggak ada ya, karena sudah mulai fokus memang buat ngerjain demo day-nya, jadi nggak ada kuis. Terus untuk tugasnya minggu ini assignment itu tulis nanti kita kasih 2 soal, terus ditulis minimal 300 kata hingga maksimal 500 kata dalam bentuk PDF. Jadi ada 2 soal itu, yang pertama di mana implementasi pada PCA dan jelaskan, terus yang kedua jelaskan perbedaan PCA dengan algoritma lain. Itu deadline-nya masih sampai tanggal 26 Juli. Nanti aku langsung masukin di Google Classroom hari ini. Oke, untuk materi besok kita langsung bahas penggunaan PCA. Jadi di materi besok kita fokus langsung ke PCA-nya. Jadi nggak kayak hari ini, kemarin kita masih harus bahas matematikanya. Jadi besok kita bakal fokus ke PCA-nya. Kita langsung akan lihat apa itu PCA, kapan kita pakai PCA, terus impact kalau kita pakai PCA itu apa, gitu. Jadi besok kita udah fokus langsung ke PCA-nya dan coding di supervised learning pakai PCA. Oke. Kalau memang tidak ada yang bertanya, ini udah jam 21.48. Kita bisa akhirin kelas hari ini karena memang harusnya kan selesainya jam 21.45 ya. Itu boleh dibaca-baca lagi gitu, nanti bisa ditonton ulang lagi materi-materinya. Karena emang berat banget materi PCA. Oke. Kalau kita aku izin untuk stop share screen kalau memang nggak ada yang bertanya. Jangan lupa juga untuk deadline pengumpulan proposalnya ya. Jangan lupa untuk deadline pengumpulan proposalnya. Kayaknya deadline pengumpulan proposal itu hari ini ya. Oke. Yang bisa open cam boleh open cam mungkin. Kumpulinya perwakilan aja ya, perwakilan. Kalau memang ada yang salah kumpul boleh dikumpul ulang ya. Jadi yang nanti kita ambil yang terakhir gitu, yang dikumpulkan terakhir. Jadi kalau memang masih ada yang salah boleh dikumpulin ulang. Oke. Karena cuma satu layar, oke, kita screenshot ya. 1, 2, 3. Oke. Makasih buat teman-teman yang udah datang di kelas hari ini. Kita akhiri kelas hari ini. Nanti bisa dieksplor lagi tentang materi hari ini ya. Besok kita langsung gimana implementnya aja gitu. Baik, selamat malam dan terima kasih semuanya.